Okay, so this is part two of the presentation on our fast exact simulation algorithm for the first passage event of a general subordinator. In part one, I described the algorithm and discussed its computational complexity. In this video, I will recall the algorithm briefly and then discuss the elements and ideas behind the proof of the complexity result, and show you also some numerical examples that are related to our motivation and interest in these type of problems. Okay, so you will recall from the previous video that the main actor here is this triplet. So the time a subordinator crosses a given boundary function, the position just before it crosses, and the position where it lands. In other words, the algorithm samples from this triplet. It is exact, so samples exactly from the law, and it is efficient in that it has the running time, which is random, has all moments. Okay, so recall briefly the structure of the class of subordinators this applies to. This is infinite activity subordinators, which close to zero are of this type. So are of the type of stable, tempered stable, where tempering parameter can be zero or can be strictly positive, and the truncation parameter R is important. It's always a positive, possibly very tiny number. The subordinator this corresponds to is going to be called Y in the next slide, and has jumps at most R. On the other hand, the compound Poisson process that corresponds to lambda R will have jumps of arbitrary size, including possibly very small. Okay, this is a general class of subordinators, as I said in the previous presentation, because if you look at, if this thing happens to have a density, the Levy measured at zero, then this only depends on the limiting behavior of this density at zero, not on any particular value, finite value. Okay, this is the algorithm. You see, we have this decomposition of Z into truncated tempered stable and compound Poisson, and the algorithm cycles, right? So it starts with a boundary function C, and then it will record crossings over smaller levels than C, possibly, right? And the levels are all smaller than the truncation parameter in Y, which is this R. Remember, rho is typically 1/2. It's a parameter between 0 and 0.5. And what it does, it samples the first jump time and jump size of the compound Poisson process Q, and samples this triplet for B, for this lower barrier function B, for the truncated tempered stable Y, and then it updates if Y crossed barrier B before Q jumped. It updates, shifts the problem in time and in space, reducing the barrier, and then cycles through. And then if Q jumps before Y has managed to cross, then we need to sample Y conditional on being below the barrier, right, where this is a random value that's going to be potentially very small. I discussed this in the previous video. And then the update happens in that case based on the sum of the sample from the conditional law of Y. It's the first jump time plus the jump itself. Of course, this is the update by which we reduce the barrier and shift the time. Okay. So that's the algorithm. Now we're interested in its complexity. You see, this will sort of cycle. You don't know how many times it will go through, right? So we need to somehow control that. And in order to control it, we need to look at the global picture. So we take the barrier and the subordinator on the interval from 0, the time interval from 0 to the crossing time, okay? And in that interval, there will be a k, which is a random number of jumps of the compound Poisson component Q in this interval. So the dependence between Q and this time, of course, is a priori very complicated, because Q contributes to the crossing time of Z, obviously. But nevertheless, there's going to be a finite number of jumps, random number, and there's going to be these epochs at which these jumps occur. Like, for example, this is the second jump of Q, this is the third jump of Q. Now, what does the algorithm do between these jumps of Q? Well, between the jumps, what is possible happens is that Y, the truncated tempered stable guy, jumps across the function B, okay, the function B. This is recorded by these times that happen, finite number of times that happen between two consecutive jumps of Q, okay. And so these times are there, and what we need to do now is we need to write down this increasing sequence of times. Okay, there's going to be finitely many of them. There's going to be k is the number of times of the compound-Poisson process, and we need to on one hand find the bound on k, and we have to in fact do in the proof, if you look in the paper, I don't have a slide on this, but in the paper you will see that k needs to be bounded in two ways, because each of the bounds sort of deteriorates in certain regimes, but in actual fact, in order to get closer to the real behavior, one needs both of these bounds, because the minimum of the bounds is smaller than either of the two bounds in certain regimes. Okay, so that's one element. Another element is that in each of these time intervals, the workload, in other words, how much effort running time, what our running time is going to be, is actually these values are dependent. They're not independent, because you see, when, for example, y jumps over b here, it depends what the overshoot is, okay, and as to what the next starting point will be and what the next problem will look like. So these problems are nested. And this dependence, we had to develop a simple but effective adapted method for bounding this. In other words, the workload, so the running times between these times are not IID, of course. And they cannot be bounded by anything IID. One really needs to look at this sort of adapted behavior. And then, but in order for this to work, one has to have some uniformity of the algorithms that one uses in each of these steps. And of course, this we do have, because as I discussed in the previous presentation, this conditional truncated tempered stable guy being small can be sampled by sampling the tempered stable guy being small, and that's essentially equivalent to being able to sample stable variable conditional on being small, which is effectively done by de Vroij's algorithm that covers all concave densities in a uniform way, and this gives you a uniform bound on this sampling scheme. And the other extremely important component in all this is the bound that we obtained. So for sampling this triplet, of course, this is reduced to sampling the tempered stable. You see, remember, this is truncated tempered stable, sampling the tempered stable triplet, which we've developed recently, and we've obtained an algorithm that has an exponential moment, and therefore all moments of so the running time of the algorithm has an exponential moment, and therefore all moments all moments are finite. And in particular, we have explicit control on the expected running time in the tempered stable case. Okay, so that's another component that is important in this proof, and that plus this sort of dependence interlacing lemma that we have in the paper yields the complexity that presented in the previous video. Okay. Now, so now one can have a little bit of fun with this algorithm. For example, if we choose Z to be stable, okay, so its Levy measure is proportional to this, we can nevertheless decompose it in the way and stick it into our class, right? So we make it tempered stable around 0, and then perturb this tempered stable by a finite activity compound Poisson process, right? So this compound Poisson process is, of course, for x greater than 1, it has to be exactly stable-like, and between 0 and 1, this has to be of this type, and this, of course, integrable at 0, right? So then one knows in this case the law of the crossing time, because this is if the level is constant, the law of the crossing time is the same as the law of this random variable, where Z1 is just stable. Okay? And so one can, of course, sample it directly. On the other hand, one can sample it using our algorithm 1. So one can compare the two empirical CDFs. Here's the comparison. You see they lie one on top of the other. So the blue one is empirical CDF from our algorithm, and this is empirical CDF. The other is empirical CDF from the sample. So, of course, one doesn't see much of a picture like this. It's natural to construct the Kolmogorov-Smirnov statistic and to look at the trajectory that one gets, which should resemble trajectory of a Brownian bridge. And this is based on 100,000 samples, and you see that this is really looks exactly like Brownian bridge. So this would pass Kolmogorov-Smirnov test without any problems. Okay, so that's just a fun test to see that our algorithm implementation seems to be making sense. Now, really, the motivation for us for doing this is because we're interested in Monte Carlo approximation of fractional partial differential equations of the following type. Okay, so it's a very simple incarnation of the problem that we're interested in. So I take a Feller process with a Feller generator AX, and then here, instead of a partial time derivative, I use a generalized Caputo operator of order at most 1, which corresponds to this formula, which is given via this Levy measure on 0 infinity, and the fact that it's of order at most 1 corresponds to the fact that this integral is finite. In other words, this nu exactly generates it's a Levy measure of a subordinate. It's a Levy measure of a subordinate. See, phi is the initial value function. Right? And indeed, in order to sort of make a Monte Carlo approximation for a solution of this, so set it up, one needs a Feynman-Katz formula, which is of course well known. I will now describe it briefly. So one really first looks at this type of process, which is a subordinator in S, generated by nu, so this is a driftless subordinator generated by nu, and this quantity Tt is exactly the first passage quantity of this subordinator over this fixed level T minus A. Now, with that in mind, it turns out that if this subordinator is independent of the Feller process X, then this stochastic representation is the Feynman-Katz formula for the solution. And indeed, you see, this is then a natural estimator for this, because these two time and Feller process are independent, and this we can sample exactly from using our algorithm, right? It's exactly our algorithm is designed to do this. And X, either we can sample X exactly at its marginals at a given time, or we need to sort of approximate those margins. Right? So in order to have a little bit of illustration how that would work in practice, we pick a two-dimensional problem, right, where phi is x1 plus x2 squared, let's say, and this is a planar Ornstein-Uhlenbeck process with some parameters. It's, of course, well known that this guy here is Gaussian with mean and variance. Given t, we know it given the other parameters, so this will mean that our estimator will be unbiased. It will have the expectation of the estimator will be exactly the value that we're trying to estimate. And then here we just chose something that looks non-trivial, right? Generalized Caputo operator of this type, which sort of fits in our framework, right? So this is tempered stable in 0, 1, and then it has some sort of decay later on. You just read the parameters of this representation from u, and then because we now know how to simulate this exactly, and as I say, this guy has a normal distribution given the time to tt, which is given mean variance as a function of t, we can obtain, we can simulate this quantity, and this estimator is an unbiased estimator of this solution. Okay, and here's a slice of this solution, right? So at time 5, you see this two-dimensional thing. This is something that would be very difficult to compute in any other way. Of course, this example that I presented, we didn't study the computational complexity of this Monte Carlo approximation given a tolerance level of error level, right? But now the whole idea of developing our algorithm 1 and understanding exactly its computational complexity is motivated by our desire to actually analyze these such Monte Carlo schemes and their generalizations in detail, and give a priori guarantees for the computational complexity given tolerance epsilon. There are many generalizations possible. I mean, here one can look at bounded domains. One can look at also dependence between T, the subordinator, and the process X, and try to simulate that jointly, etc., etc. But all this is something that is left for future work. This is just a numerical example that illustrates our algorithm in action. Right. So finally, okay, so this paper is the paper that does the template stable guide, which we put out a couple of months ago. The current paper, where the algorithm 1 is described and analyzed, you can find the archive link on my webpage. Also, this presentation is on this website, and we have Python and Julia code for algorithm 1 in this presentation, which of course uses the Python and Julia code for the algorithm in development for paper 1. Everything is on GitHub, and the links are embedded in this PDF. Okay, I hope you enjoyed this presentation. Thank you very much for your attention.